What if I told you that a simple experiment using just two slits and a beam of light completely changed how we understand the universe? This is Double-Slit Experiment. A test so simple yet so mysterious that it shattered the boundary between classical and the quantum world. In modern physics, the Double-Slit Experiment demonstrates that light and matter can behave both as particle and wave. It was first described by Thomas Young in 1801, who used to argue that light behaves as a wave. More than a century later, in 1927, Davison and Gamma and independently judged Paget Thompson revealed that electrons, particles of matter, also show the same behavior. Later, that experiment was extended to atoms and even more complex molecules. The experiment belongs to a family of double-path interference experiments, where a wave splits into two and recombines. When their path differs, the result interference produces regions of brightness and darkness, a physical fingerprint of wave behavior. In its simplest form, a laser beam shines into a barrier of two parallel slits. On the screen behind it, we see an interference pattern, bright and dark fringes, caused by wave overlapping. But here's a twist. When observed closely, the light hits the screen as the individual photons, tiny particles building up at the same time one by one. It is as if nature can't decide whether light is a wave or particle until we look. In 1801, Thomas Young presented his famous paper on theory of light and colors to the Royal Society, explaining interference patterns like Newton's ring using wave interference. His double-slit setup allows light to pass through two slits and interfere on a screen, providing light behave as a wave. This directly challenged Isaac Newton's corpuscular theory, which claimed light consists of particles. Young's demonstration was revolutionary. It gave birth to the wave theory of light. However, a century later, discoveries like the photoelectric effect showed that light sometimes behaves as discrete packets, or photons. This contradiction gave rise to the concept of wave-particle duality, forcing physicists to rethink reality itself. It's like the universe behaves differently depending on whether you're watching or not. So, that single idea reshaped everything we understand about quantum physics. When two slits are illuminated by a coherent light source, such as a laser, light from both slits spread out and overlaps on the screen behind them. We didn't just see two bright spots. Instead, we see an elegant pattern of alternating light and dark fringes appear, the result of interference. Each slit acts as a secondary source of wave. Where the peak of the wave meets, they amplify each other, producing light bands known as the constructive interference. Where a peak meets a trough, they cancel each other out, producing dark regions called the destructive interference. The spacing and the brightness of these fringes depend on the wavelength of the light and the distance between the two slits. The narrower the slit or the shorter the wavelength, the wider the spread of the pattern. This is why even in a simple single slit experiment, light doesn't just form a shadow, it produces a diffraction pattern that spreads outward, a behavior only wave can show. If light were purely a stream of particles, the result would be different. So, we would actually see two bright lines corresponding to the two slits. Each particle will pass through one slit or the other, but that is not what happens. The actual experiment gave us a wave-like interference pattern, even when particles go through the slits one by one. This single observation breaks the wall between classical and the quantum physics, proving that light cannot be described as only a particle or only a wave. It must be something deeper. A quantum object that behaves as both depending on how we measure it. In mathematical terms, the intensity of the light on the screen can be described by the superposition principle, where the distance between the slit is d and the wavelength is lambda. The brightness fringe appear at angles given by. This simple equation governs the entire phenomenon, determining where bright and dark bands will form. It is a perfect demonstration of the harmony between mathematics and physical reality, a window into the underlying order of nature. It's like every particle is a traveler, exploring every possible path in the universe, until observation forces it to choose one. Over the years, scientists have recreated and redefined the double-slit experiment in countless ways, each new version revealing something even stranger about the universe. When the intensity of the light is lowered so much that only one photon passes through at the time, something astonishing happens. Each photon appears as a tiny dot on the screen, as though it behaves like a classical particle. But as these dots accumulate over time, they form the same interference pattern as before. This means that each individual photon somehow interferes with itself, as though it passes through both slits at once. A mind-bending property that defies classical reasoning is a direct experimental proof of wave-particle duality. The idea that all matter, light, electron, even molecules can behave as both waves and particles. In 1927, Davidson and Gamma and George Paget Thompson confirmed that electrons, which we usually think of as particles, also form interference pattern when passes through a crystal or a double-slit setup. Later, the same phenomenon was demonstrated using atoms and molecules, showing that wave behavior extends to all matter. The larger the object, the harder it is to observe, but not impossible. In 2001, scientists successfully performed the double-slit experiment using this thing on the screen, because I don't know how to pronounce the name. So it's actually molecules. Carbon spheres made of 60 atoms each. By 2011, the experiment has been done with molecules containing over 430 atoms. By 2019, with over 2,000 atoms. Each time, the interference pattern proved that quantum mechanics govern the microscopic and the macroscopic world alike. In 1968, Pfliger and Mandel demonstrated that interference using two complete separate laser sources. This was groundbreaking because it showed that even independent light sources can interfere as long as they share a coherent relationship, reinforcing the wave nature of light. In 1972, researchers showed that even when only one slit is open at a time, interference can still occur. This is possible when the photon's path information is erased, meaning the photon doesn't know which slit to pass through. This is remarkable, finding it that knowledge itself or lack of it plays a role in quantum behavior. By the early 2000s, scientists have used electron field emission source and nanoscale slit structure to test quantum interference with unpredictable precision. In 2002, a coherent electron wave emitted from two nearby sites on a metal needle created an interference pattern in a vacuum. In 2017, researchers developed light-induced electron emitters, allowing them to select emission sites as small as 10 nanometers, effectively creating controllable nanoscale double slits. When one of the emission sites was turned off, the interference vanished, proving that interference depends on superposition, not on the classical presence of slits. Each evolution of the experiment revealed the same truth in different forms. Nature is fundamentally quantum, and the observation changes everything. To understand the double-slit experiment from a different angle, physicists often turn on the Mach Zehnder interferometer, a more controlled and elegant version of the same concept. Instead of two slits, the setup used beam splitters and mirrors to divide and recombine light. So, let's break it down, and here's how it works. A photon from a laser entered the first beam splitter, which divided into two possible parts, the upper and the lower arms of the interferometer. The photons doesn't just choose one part, it exists in the quantum superposition of both simultaneously. The two parts then reflect off mirrors and never meet again at the second beam splitter. At this point, the component of the photon's wave function interfere, determining which of the two detectors it will hit. When both parts are open, interference causes the photon to always hit one specific detector, say the one on the right and never the other. But if one part is blocked or measured, the interference disappears and the photons randomly hit either detector with equal probability. This behavior reveals something deeply unsettling about the quantum world. The photons doesn't just travel one path or another until a measurement forces it to. Before that moment, it is literally in a superposition both possibilities. Mathematically, this system can be described using simple linear algebra in 2 dimensions rather than just complex wave equations. This simplification allows physicists to model quantum interference precisely, making the Mach Zehnder interferometer a crucial tool in studying quantum optics and coherence, and quantum information processing. In essence, it shows that the act of observation is not passive. It changes outcome. What was once a smooth of wave probability collapsed into a single definite result. The mysterious process we call the wave function collapse. Over the decades, scientists have pushed this experiment into extraordinary limits. In 1967, Pflegel and Mandel demonstrate interference using two separate lasers, proving that the coherence can exist between independent sources. In 1972, even when only slit was open at the time, interference appeared as long as the path information was hidden. In 1991, Carnell and Molnick used helium atoms, confirming that matter waves behave like light. In 1999, buckyball molecules, 60 carbon atoms each, produced interference fringe, showing quantum effect at the molecular scale. In 2002 to 2017, electron field emitters and nanoscale experiments continue to refine our understanding of quantum interference. And in 2019, molecules up to 2000 atoms showed interference, proof that the quantum mechanics extend to the microscopic world. So, each new version deepened the mystery. The law of physics seems to change one observation enters the picture. In classical terms, light behavior in the double-slit setup can be modeled using the Huygens-Fresnel principle, which says every point in a wavefront generates tiny secondary wave. The pattern on the screen results from their superposition, their amplitude adding up or cancelling out depending on the phase difference. When the two waves travel distance that differs by the whole wavelength, they reinforce each other, creating bright fringes. When they are out of the phase by half of a wavelength, they cancel, producing darkness. So this is a formula for fringe spacing is given by this equation, where the z is the distance on the screen and the lambda is the wavelength of the light and the d is the distance between slits. The relationship elegant explains how changing wavelength or splitting spacing alters the pattern, the perfect blend of geometry and wave physics. You see, the double-slit experiment isn't just about electron or light or even reality itself. So that experiment actually whispers to us that the universe behaves differently whether you're watching or not. The double-slit experiment stands as one of the most profound demonstrations in all of physics, from Young's early observation of light waves to modern quantum studies involving atoms and molecules. It shattered our classical understanding of nature. It showed us that matter isn't simply solid or wave-like, but both at once, and that observation plays an active role in determining outcomes. Even today, no one fully understands why the act of measurement collapses the wave function. It's a mystery that lies in the art of quantum theory. As Richard Feynman once said, the double-slit experiment contains the only mystery. We cannot make the mystery go away by explaining how it works, because we do not know how it works. Through two tiny slits, humankind discovered that the universe is not determined but probabilistic, a realm of endless possibilities until someone looks. The double-slit experiment isn't just changed physics, it changed how we see reality itself. So, if you do like this video, please do like to share, like and subscribe, and comment down what you think about the double-slit experiment. See you next time on this channel, and stay curious.